In this video, we're going to discuss Bayes' theorem and how we can use tree diagrams to help us use Bayes' theorem. So first of all, just to sort of talk about what a tree diagram is. So when we have experiments that consist of a bunch of different steps, where each step has different options, and future steps sort of depend on what happens in the previous step, it's very useful sometimes to visualize them as using a tree diagram. So the idea here is that you have various possibilities. So you'd have step 1, okay, with some possibilities. And then from step 1, maybe there's other possibilities that could happen in step 2. And then each branch is going to have probabilities on it to say the probability that you take that branch. So let's try an example where this is useful. So suppose we have a box that has 3 yellow and 5 blue marbles, and we're conducting the following experiment. So how the experiment goes is we're going to randomly select a marble out of the box and record the color. Okay, so we care about what the color is. Now, if the marble was yellow, then we're going to remove it and add 1 blue, and then draw again and record the color again. If the marble was blue, then we're going to remove it, add 3 yellows, and then draw again and record the color. So you can see here that it matters what color we get on our first draw as to the probabilities for the second draw. So this is a case where a tree diagram will be very useful. So my first step in my tree diagram is to pick a marble. Okay, so in my options, I either get a yellow one or I get a blue one. So I'm calling this yellow Y1 and B1 to mean that it's my first draw. Okay, so this is draw 1. Now on the first draw, there are 3 yellows and 5 blues. So the probability I get a yellow is going to be 3 out of 8, because there's 8 marbles in total. The probability I get a blue is going to be 5 out of 8. Now notice when these probabilities on each sort of branching, they add up to 1, because we either have to get a yellow or we have to get a blue. So exactly one of these things needs to happen. Okay, now if I got a yellow one, my next step, I'm going to do some stuff to the box distribution, but then I'm going to pick again, and I'm either going to get a yellow or a blue. Okay, same with if I get a blue on the first draw, I'm going to pick again, and I'm either going to get a yellow or a blue. Okay, so my next step is the second draw. Okay, so draw 2. Now, it might be useful to help us write what is the box going to look like in this case. So if I got a yellow one, okay, my first marble was yellow, I'm going to remove it and add a blue one. Okay, so I used to have 3 yellows, but I'm going to remove it, so now I have 2 yellows. And I had 5 blue, but I'm going to add 1 extra blue, so now I have 6 blues. So the probability that I get a yellow on my second draw is now going to be 2 out of 8, or 1 out of 4 if we reduce. And the probability I get a blue is going to be 6 out of 8, or 3 out of 4. Notice again, these probabilities on this branching sum to 1. Okay, so that should always happen. Now, if I happen to get a blue on the first draw, what the box is going to look like is I'm going to have, so I did have 3 yellows. Okay, so if I got a blue one, we're going to remove it and add 3 yellows. So I used to have 3 yellows. I'm going to add 3 more yellows. So now, oops, not 3. So now I'm going to have 6 yellows. And I had 5 blues, but I'm going to remove 1, so now I have 4 blues. So I have 10 marbles in total. The probability I get a yellow is 6 out of 10, or 3 out of 5. And the probability I get a blue is going to be 4 out of 10, or 2 out of 5. And again, notice these sum to 1. Okay, so this is what our tree diagram looks like. This is our entire experiment. And now, once we have it, we can compute a lot of things. Now, one thing I do want to point out, though, is these probabilities that are further in the tree, so further along, they're all conditional. So for instance, this 2 over 8 or 1 over 4, this is the probability that we get a yellow on the second draw, so y2 happens, given that y1 happened. Okay, so down here, this 3 over 4 is the probability that we get a blue on the second draw, given that we got a yellow on the first draw. Okay, now if you remember, so maybe I'll write recall here. If we rearrange the conditional formula, the probability of A intersect B was the probability of A times the probability of B given A. Okay, so now if we multiply along a path, so I'm going to take this path here, this first probability, the 3 over 8, this is just the probability that y1 happens. So not conditional, it's the first thing that we do. So it's the probability of y1 multiplied by the probability of b2 given y1. So that's just looks like this. So it's actually the intersection probability. So multiplying along a branch gives us the intersection of those events. Okay, this is very useful. So for instance, if we wanted the probability both marbles are yellow, so that's going to be the probability of y1 intersect y2. So we get a yellow on the first draw, and we get a yellow on the second draw. This is just, so I'm going to highlight it, this is just this path. So I get yellow 1 and then yellow 2. That's the only way I can do it. So it's going to be the probability of y1 times the probability of y2 given y1, which we have both of these. So we just multiply along the branch. So it's 3 over 8 times 2 over 8, or 1 over 4. And I'm going to get 3 over 32 as my probability. Now, what if I want the probability the second marble is yellow? Okay, so this is just the probability of y2. Okay, we do not have that on the tree explicitly, but if I think about y2, how could it happen? Well, I either get y1 and then y2, or I got b1 and then y2. Now this first one is the one that we already did. Okay, so that's our blue one. And this b1 intersect y2, I'm going to call it green, so it's going to be this path here. So both of those together make up the probability of y2. So what I did was I found y2 on my diagram, and I'm adding up the paths that get to y2, so that pass through y2. So this one we already did. It was 3 out of 32, and b1 intersect y2 is going to be 5 out of 8 times 3 out of 5. So it's actually 3 out of 8. Putting those together, you get 15 over 32. Okay. Now, what about part D? What is the probability the first marble drawn is yellow if the second marble drawn is yellow? Okay, so this if part, okay, this is the thing that we know. We know that this is going to happen, and we want to know the probability the first marble is yellow. This is a conditional probability. So what I'm looking for is the probability of yellow 1 given that yellow 2 happened. Okay, so remember, the second one is the one that we know. The first one is the one that we want. Okay, so now if I use the conditional formula, this is the intersection of the two divided by the probability of the one that we know. And we actually already computed both of these. Okay, so probability of y2, that was part C. And the probability of y1 intersect y2, that's the blue, that's part B. So all I have to do is divide these two probabilities. So 3 out of 32 divided by 15 out of 32. So that's 3 out of 15, or 1 out of 5. Okay, which happens to be 0.2 if you like decimals better. Okay, now I'm going to point out here, without knowing it, we actually just use Bayes' theorem. Okay, so I'm later going to encourage you not to memorize the formula or even try to use the formula, but there will be one. And just try to use the tree. So all you need to know is the conditional, the formula for the conditional, and then using the tree to find each of these bits. Okay, let's try one more. What is the probability the second marble drawn is yellow if the first marble drawn is yellow? So all they've done here is change the order. Okay, it's still a conditional, but now we want the probability of y2 given y1. Okay, now y1 is early in the tree, right? This is one of our first steps. Okay, y2 is later. So in fact, this is explicitly on the tree. So I'm going to go up here. So I know that y1 happened. Okay, that means I know I went up this branch. And I want to know what's the probability that I got this branch. So I went up to yellow 2. That's this probability here. So we actually already computed it just by assuming that y1 happened. So this one is just 1 over 4. Okay, so explicitly determined in the tree. Now, if you forget, if you don't realize that, and you decide to try to compute it, so probability of y2 and y1 over the probability of y1, you're going to get the exact same thing. So this is 3 over 32. Now the probability of y1 is the first thing, so that's this probability here, so 3 over 8. So we should get exactly the same thing. So if I flip the bottom and multiply, I'm going to have the 3's are going to cancel, and I get 8 over 32, which is the same as 1 over 4. So if you don't notice that it is a thing you've already computed in the tree, it's fine. The formula will still work, and you'll get the same answer. But obviously it's faster if you do notice that you already had it. So we use Bayes' theorem without even knowing it, but here I'm going to try and give it to you. Let me just make this a bit smaller. So this isn't even the most general that it could be. Okay, so it could be even better than this. But let's assume that we have events B1, B2 to Bn, and they're all mutually exclusive events. So that means they can never happen at the same time. And if we know that the union of them is the sample space, so that means that exactly one of them needs to happen, then we can say for any event in S, we can compute the probability of B1 given the event A. Okay, so this is kind of hard to see what's going on, so I'm going to try and draw you a picture. So the idea is your first sort of step, if you use a tree, is the B's. Okay, so the B's, exactly one of them has to happen. Okay, so that's your first step, and then you have event A. So either event A happens with each B or it doesn't. Okay, so I have A and A complement. A complement. Okay, so what's going on here, and I'm going to write this in blue, but the actual form is going to be in purple. Okay, so the conditional formula says that this should be the probability of B1 and A divided by the probability of A. Okay, now I'm going to try and do these in colors here. So let's call this one blue and this one, say, yellow. Okay, so B1 intersect A is just this path here. But A happens in lots of ways. Okay, so A, I want all these yellow paths, so every path that has an A in it. So I have to take a path for every B that there is. There's going to be one path. And then I could add those up. Okay, now remember what the probabilities look like. So this one is going to be probability of B1. And this one here is going to be the probability of A given B1. So the opposite probability from what we're actually trying to compute here. So this is what Bayes' rule says. So the probability of B1 given A should be the probability of B1 times the probability of A given B1 all over, now I need a huge line, because I need to add up all the different ways that A could happen. Okay, so A could happen with B1, A could happen with B2, okay, or it could happen all the way with Bn. Okay, so I think I got all those. Now be careful, so just to remind you, okay, so this probability on the top is just the intersection. B1 oops, not A yet, intersect A. Okay, and on the bottom here, this is again B1 intersect A. And then I'm going to add B2 intersect A. Okay, and you'd add all these intersections. So Bn intersect A. And you can do these for all the events. Okay, so here the next one, I mean, you can do this for any of the B's. So it's going to look the same, so, but here the top is going to be our B2. So B2 and A. And then the bottom is going to be the same as it was above. So B1 times the probability of A given B1 plus B2 times the probability of A given B2, okay, all the way to Bn. This is a PR. Okay, so it looks ugly. Now, one thing I do want to sort of point out here, maybe I'll do it in blue, or actually let's get a different highlighter color, can I? Yeah. So you'll notice when you're doing these that the probability on the top appears on the bottom. Okay, this is not unusual. That always happens because the top is sort of a specific way that the event A happens, and the bottom contains all the ways that A happens. So that specific one, or the specific ones, should be there. Now, the reason why I say this is not as general as it could be is because the top could have multiple things as well. Okay, so you might need to add multiple cases on the top, as we're going to see in the next example. Okay, but this is what Bayes' theorem looks like. My note here is this is ugly. Okay, I hate using it. I never do. So I think we should use a tree instead. Use a tree with the conditional probability formula. Okay, and then there's no need to remember this. Okay, but that's what it looks like. So let's try another one. So suppose we have this fake data that compared Canadian political alignments with ages. Okay, so for some election year. And voters that didn't align with one of the four main parties were just discarded. Okay, so we didn't worry about those ones. So here we have the age bracket. Okay, so 18 to 29, 30 to 44, and then 45 and over. And then each age bracket is split into the percentage of people that voted for each of the parties. Now, if you notice, if you look at these rows, okay, they add to 100%. So what that means is these probabilities are not intersections. They're actually conditional probability. And they're conditioned on what age you're in. Okay, so this gives probability of party given age. Okay, so you want to be careful about that. But that's what this is doing. And then we know that 15% of the voters were 18 to 29 and 23% were 30 to 44. So they're telling us specific probabilities for the different age brackets. Okay, now what we're looking for, okay, so what we want, so suppose we randomly select a voter who voted NDP. Okay, so we know they voted NDP, and we want to know the probability that they're 44 or younger. Okay, so this is a conditional probability. So we want to know that they are less than or equal to 44, given that they voted NDP. Okay, that's what we're looking for. How we're going to find it, I'm going to make a tree diagram. Now, the hardest part about the tree diagrams is to know sometimes what the first sort of branching should be. The way I like to think about it is there's two things to note. Okay, so here we have some conditional probabilities. When you have conditional probabilities, they're going to be further along in the tree. Okay, so what do we need to know? We need to know what age category they are. Okay, so that means age is going to be our first branching. Another way you can tell here is that they gave us, here, maybe I'll just write on here. So 15% of voters are 18 to 29. So they told us the probability that you're 18 to 29 is 0.15. Okay, so they told us the age probabilities. Okay, so though without any condition. Okay, so then we have the probabilities on the first branching. So both of these facts help me to determine that I want to split by age first. Okay, so I want to do age. So I have 18 to 29, 30 to 44, and then 45 plus. And we know these probabilities. So actually maybe I'll do them in a different color so they stand out. So there's 15% chance that you were 18 to 29, 23% chance that you were 30 to 44. So the way that we find this missing one that they didn't give is that these need to add to 1. Okay, so we're going to do 1 minus the others. So 1 minus 0.15 minus 0.23. And I think that we get 0.62 there. Okay, now the next step, it should be, okay, the parties. Now, so then you might think, okay, there's 4 parties, so we have to go 4 different branchings on each. Okay, now you could do it this way. That gives you the most information, but we only have one question here, and it only cares about whether we get NDP or not. So to save some time, instead of doing all 4, all I'm going to do is they voted NDP or they did not vote NDP. So I'm just going to split it into 2. Okay, and then I want to put the probability. So the probability if you're 18 to 29 that you voted NDP was 0.35. If you were 30 to 44, it was 30%, so 0.3. And if you were 45 and over, it was 0.2. And then we can compute these other the other probabilities, by either doing 1 minus the one that's already there, or adding up the other categories. Okay, either way you get the same answer. So this first one should be 0.65. In the 30 to 44 category, it was a 70% chance, and in the 45 plus category, it was an 80% chance. So now what we're looking for is the probability that you were at most 44, given that you voted NDP, so N occurred. So using the conditional formula, this is the intersection, so you were at most 44 and they voted NDP, divided by the probability that they voted NDP. And then for the numerator, if they're less than or equal to 44, they could have been in the 18 to 29 category, or they could have been in the 30 to 44 category. Over the probability. So 18 to 29 is this top one. Okay. 30 to 44 is this middle one here. And then let's do yellow. So then all the ones that have an N are the NDP. That's the probability of N. Okay, so that's all we need to do here. So notice on the top, though, I have two different things added up. So this is going to be 0.15 times 0.35 plus 0.23 times 0.3. And then on the bottom, I have those two terms again. And then the additional term of 0.62 times 0.2. Okay, now if you compute this, I think you get 0.1215 on the top and 0.2455. So I think it simplifies to 0.4949. So there's about a 49% chance, if you know they voted NDP, that they were less than or equal to 44, so less than 45. So this is using Bayes' rule. Okay, we definitely use Bayes' theorem here. We just didn't explicitly apply the formula because if we use the tree, we don't really need it. So I want to do one more example. This one involves a little bit of terminology. So this is often used when you're testing populations for things. So you have this idea of false positive and false negative. Okay, so this can be confusing. So what we mean by false positive is the test is positive, okay, but wrong. Okay, so it's incorrect. And then false negative here is the test is negative, okay, but incorrect or wrong. Okay, so if C, let's define C to be has condition, whatever it may be. Okay, and I'm going to use plus here for test positive. Okay, and minus for test negative. Now I'm going to warn you, especially in some stats classes, they use true positive and test positive. I don't like to use this word positive in more than one way. So that's why I'm using has condition. Okay, so then C complement doesn't have condition. Okay, so these are like the true ones. Oops. So you know, if you're in C, you know you have the condition, okay? So you could have the condition and get a negative test. That's fine. It just that's the example where you get a false negative. Okay, so then the false positive, the idea here is that so it's the probability that you get a positive test result, but it's wrong. So that means that you didn't have the condition. So you were in C complement. Okay, so this means test was wrong. So we knew that you didn't have the disease, but we still got a positive test. Okay, so similarly, false negative, this is that you get a negative test result, but you know you have the disease. Okay, so you know you have the whatever, it doesn't have to be disease, I shouldn't use that. You know you have the condition, whatever it is, but you still get a negative test. So that would be a false negative. So let's do an example using these. So during the quarantine, say the college noticed that it was hit by a plague of clinomania. So this is defined to be the excessive desire to stay in bed. Suppose 6% of students, I shouldn't say on campus, but you know what I mean. 6% of Camosun students suffered from this affliction, and we develop a test for it, but the test is not perfect, okay? No test is perfect usually. So it has a false negative rate of 1% and a false positive rate of 2%. Okay, so they tell us some things. Now, Sydney gets tested for clinomania and tests positive. Okay, so here we know she has a positive test result, and we want to know what's the probability she actually has clinomania. So what we're looking for here is the probability that she has clinomania given that she got a positive test result. Okay, so it's the conditional probability. So I'm going to make a tree diagram. And again, here it's hard to tell what to put first. Okay, but we know 6% of students have the clinomania. So what they've told us is the probability of C is 0.06, which means the probability of C complement is 0.94. So because we know C, it's very likely that C is the thing we want to come first in our tree. Okay, so I'm going to do, you either have the condition or you don't have the condition. And then the second step is your test result. So you either get a positive or negative test result. So this seems counterintuitive because we don't usually know if someone has the condition or not. Okay, but because we know sort of the population statistics, it can help. This is why this way works better. Okay, so this is the true result. Okay, and then the test result. Another way we know it has to go this way is because they gave us false negative, false positive rate. So we know 0.01 is a false negative. So that's the probability you got a negative test given that you had the clinomania. And the false positive rate is the probability you get a positive given that you did not have clinomania. So again, both of these depend on whether or not you have the condition, and that's why it needs to go first. So these probabilities live in the second branching over here. So let's try and put some probabilities on our tree. So we know the probability of C is 0.6, and the probability of C complement has to be 0.4. Now we want to put these conditional, these false positive, false negative things. Okay, this can be tricky, but you want to say, okay, where do I get a false negative? So that means I have to have the condition and get a negative test result. So the false negative goes here. So we know that this is 0.01. False positive means that I don't have the condition, but I get a positive test result. So the false positive goes in this spot here. So this is going to be 0.02. Okay, now these ones have to sum to 1. These ones have to sum to 1, so we can fill in the rest of our tree, 0.99 and 0.98. And now we can compute the probability we want. So C, given positive, is going to be the probability of C and positive divided by the probability of positive. Okay, so, okay, C and positive is just this branch here, whereas positive happens if you have C or if you don't have C and you get a false positive. So you always multiply along a branch and add different branches. Okay, so on the top I'm going to have 0.06 times 0.99, and on the bottom I have 0.06 times 0.99 plus 0.94 times 0.02. So if I compute these, I think I get 0.76. So given Sydney got a positive test result. Okay, so because of the inefficiencies of the test, there is only a 76% chance that she actually has clinomania. Okay, So remember, I'm just going to write a little note here in red. Okay, so you, on a tree diagram, you always multiply along branches, okay, and add different branches. Okay, and you always have to multiply all the way along. Okay, so that's how we use the tree diagram. Okay, so that's an introduction into tree diagrams and how they relate to Bayes' theorem.